Froggy, Sebastian, and the bot, what pet names may reveal about how people conceptualize AI assistance. So what I'm exploring today, and in my future paper on the subject, is a very quite small seeming behavior that I think is actually quite revealing. And that's, what do people call their AI assistants when they're not just using the official product name? So not just ChatGPT, Claude, Grok, but things like Froggy, Sebastian, my editor, the bot, the gremlin, or whatever private shorthand emerges in real use. So my argument here, it's not that AI assistants are persons. It is that the names that people give them may reveal how users are making sense of them, whether as a tool, a teammate, a creature, a clerk/Clark for British, companion, or even as a kind of extension of self. And I'm interested in this because my background is as an evolutionary anthropologist, so I'm interested in how we use tools and also how humans have evolved to use tools socially. So because these systems are increasingly present in creative and media workflows, I think this gives us a really small but useful human factors window into trust, boundaries, assignment, and expectations. I don't have my clicker. So, nice, okay. So people have always humanized artifacts. We name ships, we swear at printers, we praise our laptops as if they have loyalty or malice towards us. And of course, as I'm sure many of you know, the Roomba literature is wonderful on this with domestic robotics, because in this sense, people do not merely own robot vacuums. They very quickly end up living with what is apparently a very small circular colleague with a temperament, a habit, a pet, or in some cases has a personality problem. So naming here it's not just a trivial decoration, it's one of the ways we get to place objects in a social order. With generative AI assistance, that process, it becomes especially interesting because the systems speak in natural language. They respond in a seemingly contextual way. They mirror tone, or they can mirror tone, and they can be used for everything from drafting copy to brainstorming to emotional venting. So the question is not, do people anthropomorphize AI? The more interesting question is, how do people do it, to what degree, and for what practical purpose? Because calling an assistant Froggy is not the same social act as calling it the bot. So one sounds like a mildly cherished household entity, and the other sounds perhaps more like IT services has arrived. So calling a chatbot Sebastian with a human name also is not the same as calling it my editor. And so these names may condense assumptions about animacy, warmth, predictability, ownership, authority, usefulness, and control as well. So the conceptual background here, it comes from a few overlapping literature. So, of course, many of you will be familiar with the CASA tradition, the idea that computers are social actors, but I would caveat that personally without agency. So Nass and Moon and colleagues showed that people often respond to machines using social rules, even when they explicitly know that the machine is not human. So second, there's a broader literature on anthropomorphism, which goes much more deeply into cognitive studies and evolutionary studies as well. And this shows that people attribute human-like qualities to non-human things in variable ways, depending on context, motivation, and familiarity. So third, there is again, my very kawaii slides here. There is, of course, the Roomba and domestication literature, which I think is especially helpful when we think of LLM chatbots. So those studies showed that people often named household robots. They fitted them into routines, they assigned them personality, and they treated them as socially legible presences. And not just because they literally, or I should say not because they literally believed the Roomba was a person, but more because naming these domestic robots helped place it into ordinary life. I think pets were frequently referred to in the literature. So fourth, there's the chatbot literature itself, which shows that human-like cues can affect trust, self-disclosure, social presence, warmth, and willingness to engage. So there's already a strong body of work on anthropomorphic cues, but there's a much thinner body of work on the questions of what users themselves spontaneously call these systems once they become part of everyday life. So that's the gap that this talk and my future paper, for which I'm currently waiting out ethics approval, that's what this addresses. So one important distinction then in the talk is the difference between designer-inserted naming cues and user-generated meaning. So a lot of the research looks at what's happening when a chatbot is given a more human or less human official name, or when designs features such as avatar, tone, or persona are manipulated experimentally. So that work, of course, is very useful. But what I'm interested in is something slightly different, which is what happens after the system kind of enters a lived routine with the human in the loop. So for example, a researcher or company, they might assign a system a name like Claude, for example. So that's a top-down cue. But if a user privately starts calling the assistant Froggy, my little editor, the goblin, the bot, Sebastian, that's bottom-up meaning making. And so these two things are not interchangeable. And the first tells us whether a design cue influences our behavior. And then the second may tell us how users are already metabolizing the system in practice. So I'm proposing that pet names are nicknames that can be treated as a kind of vernacular ontology. So a compressed clue to how users are classifying a system whose status is actually neither object nor person in how they're being perceived in everyday experience. So in terms of my research questions, I've derived a set of proposed questions. And the first is, what ontological framing does a pet name imply? Is the assistant being framed as a person, a tool, a creature, a colleague, a companion, or something hybrid? Secondly, how does naming style align with role expectations? Does the user seem to position the assistant as helper, servant, editor, collaborator, clerk, tutor, novelty, or confidant? Third, what does the name suggest about trust, reliance, disclosure, and boundaries? Does it imply warm, bounded use, emotional investment, skepticism, or deliberate distancing? And then fourth, to what extent do the users socially locate the assistant? Do they imagine the assistant as male, female, neutral, non-binary, old, young, animal, species-like, ethnically marked, or maybe none of these? And fifth, do users experience the assistant as something similar to themselves, different from themselves, or even a type of extension of self? So this last point is particularly interesting to me because some users may well reject personification, completely reject it, while still talking about the AI as a drafting limb, a prosthetic memory, or an auxiliary layer of thought. So the framework here is not just about whether something feels social. It's also about how it becomes fitted into one's own cognition and routine. So my future paper, it will be conceptual and methodological rather than data-driven. So I'm not presenting a formal data set today. So what I'm proposing is this future exploratory qualitative pilot, ideally with around 50 participants using semi-structured interviews. The goal would not be population-level prevalence. It's to generate and refine a compact, reusable coding framework for naming and ontology patterns and human-AI interaction. So participants would be adults who use a generative AI assistant, at least weekly, for one or more purposes, such as for writing, planning, brainstorming, troubleshooting, decision support, information seeking, or emotional venting, which people are more and more frequently. So the interview prompts would be intentionally short and fairly concrete. What do you call your AI assistant, if anything? Why do you call it that? Do you think of it as a something, a someone, or neither? If you picture it at all, what is it like in your mind? Do you imagine it as male, female, neutral, non-binary, variable, or none of these? What do you mainly use it for? And do you think of it as an extension of yourself or not? So the basic design is small scale, qualitative, and meant to build a workable analytic instrument. So this is my preliminary taxonomy, and I'm actually very open to suggestions if anyone wants to grab me afterwards. But the main practical contribution here is this preliminary taxonomy. The first category is affectionate diminutives, so names like Froggy, Buddy, or other very softened, playful forms. And so these might suggest warmth or domestication and low-threat familiarity without necessarily granting authority to the chatbot. So the second is collaborative personification. So names like Sebastian, my editor, or my producer. So these frame the AI as a role-bearing quasi-person within a workflow. And these may or may not correlate with usefulness, offloading, and a more teammate-like stance. The third is instrumental labels, things like the bot, or the engine, or cold use of the platform name, which also might be also anthropomorphizing. So these could also overlap. So colder instrumental labels might suggest stronger ontological distance, functional orientation, and bounded trust. The fourth is non-human metaphors, animal or creature labels, gremlin, demon, or some other being that's not quite human. So this could be interesting because that might grant agency or limited agency and a temperament while still avoiding full humanization. And a fifth is ironic or resistant naming, mocking or dismissive labels that might signal skepticism, frustration, or an effort to puncture anthropomorphism. So, and then the sixth is what I mentioned is the self-extension framing, where the assistant is not merely named, but also described as a prosthetic, a mirror, a drafting limb, or an auxiliary cognitive organ, like a brain or something. So the point of this taxonomy is actually not to force names into rigid boxes, but it's to treat them as jumping off points for broader questions about ontology, tone, role, and boundary management. So why does this matter for media and creative tool teams? Well, first of all, naming patterns may offer a very lightweight diagnostic and user research. So teams should ask perhaps not only what the users think of the assistant, but what they're actually calling it when no one is watching. So that might reveal how the systems land, whether it's a clerk, a co-creator, a mascot, machine utility, or some kind of quasi-self-extension. And then secondly, onboarding language might be calibrated to the intended role. So if a team wants bounded utility, over-humanized branding may actually create the wrong expectations. If they want creative fluency and comfort, a sterile machine identity might actually push this towards this. So where naming suggests relational drift, over-disclosure or self-extension, that may indicate the name for stronger transparency and boundary clues, especially in sensitive domains. And then fifth, standards adjacent. And to conclude, the assistant does not need to be conscious for the name to matter. The name actually matters because the human using it matters. And I'm free for any questions afterwards. I'd be very interested if you want to get in touch with me about my study and what you call your personal AI. So thank you very much.
Thank you, Kathleen. And I'd now like to welcome up onto the stage Mael, who's going to talk about evaluating AI and algorithmic approaches for defect detection in archival film restoration. And a big shout out to Trinity College Dublin, who we love to have up on stage with us. So take it over, Mael.
Yeah, the clicker. Sorry, can I get the clicker, please? Hello, everyone. So my name is Mael Bonnec, and this presentation is about archive film restoration focusing on blotch detection. So our film degrades over time due to projector wear and poor storage, and this creates defects like blotches, scratches, and warping, which affect the overall viewing experience. And traditional restoration is done manually, frame by frame, which is, as you can imagine, very slow. So automated methods were developed, first using image processing, and more recently, machine learning. But detecting a dark spot in one frame isn't enough, because we need to compare with neighboring frames. So if a spot only appears only in one frame, it's like a blotch, like one in the red circle. And if it appears in the same place across the frame, it's part of the scene, like as you can see on the green circle. So, since the 1990s, image processing algorithms for blotch detection have been relied on pixel differences between frames. So the most effective method is called Spike Detection Index P, SDIp, which was introduced by Cockrum in 1990. So it's pretty old. And SDIp uses displaced pixel differences, or otherwise DPD, and it's comparing the pixel intensity in the current frame to a motion-compensated reference frame. So sudden intensity changes suggest that the dark spot is a blotch. So the RLC curve on the right-hand side here, it plots the correct detection rate in the vertical axis against the false alarm rate in the horizontal axis. So as you can see, SDIp marked with an X achieved the best balance, outperforming the original SDI, which is marked with a plus, which is performing the worst, visibly. So more recently, researchers have also turned to machine learning for blotch detection. And machine learning, just a quick recap, is a branch of artificial intelligence. And within that, one of the most widely used models for images is called convolutional neural network, or CNN. So it is designed to automatically extract and learn spatial features from the images, making it very powerful for tasks like image classification and segmentation, which is exactly what we need for detecting blotches. So in our research, we focus on a particular type of CNN, which is called UNet. So UNet is well suited for image segmentation because it captures both the fine details and the overall context. So it has two main parts. The first one is an encoding path, which compresses the image. And then we have the decoding path, which restores the detail afterwards. So to train the model, we use a loss function. Here, we're using cross entropy, which measures how well the prediction match with the ground truth. You can think of like an error score. So if the loss is higher, the worse the model is performing. So during training, the goal is to minimize this loss so the model gradually becomes more accurate over time. In previous notable research, Arthur Renaudot applied the unit model for defect detection. And unlike most other studies, his work used datasets with genuine defects, and the results were quite strong. However, there were still some challenges. In particular, motion compensation wasn't applied in his research, so which caused issues in certain scenes. And like most deep neural networks, the model required very high computational power compared to conventional algorithm, which doesn't require power. So our goal, therefore, was to design a smaller deep neural network that could still detect real blotches with fewer training samples. So we wanted to push the performance using machine learning model without relying on pre-trained network, which were often used in previous research as well. So using specific training sample is especially important. In practice, a restorer might actually manually restore just a few frames, and then those restored frames can then be used to train the model. So after that, the model can automatically restore the remaining frames, which can solve the copywriting issue for the training. So for this research, we prepared three data input data sets. The first is Cinecita on the left, which is an uncompressed format and is served as our high-quality baseline. The second in the middle is called Carrier, which is a compressed format, but still maintains a relatively high resolution. And finally, on the right, we have Night, which is a heavily compressed file with a much smaller resolution. So by using these three data sets, we were able to test our model under very different conditions. So from high-quality film scans all the way down to the low-quality, highly compressed video. So the next step was to prepare the ground truth for training. First, we need to find where the blotches are in each one of the frames. So here is the example for a Cinecita frame. Once the blotches are identified, we mask in white. Then we added a black background behind to isolate the blotches. So this is a manual work. And then, as we mentioned earlier, one of our experiments was to analyze the effect of motion compensation. To do this, we used a compositing software to compute both the motion compensation and the displaced pixel differences, or DPDs. So for illustration here, the red arrows show the direction of magnitude of pixel displacement between frames. So this helps to visualize how pixels move from one frame to the next, which is very important actually because it allows you to accurately detect real blotches. Once the input data is prepared, we can run the algorithm. First, we apply the traditional algorithm, non-machine learning method, SDIp. So by testing several thresholds, we can observe how the algorithm detection performance changes with different sensitivity settings. When it comes to the DNN, there are a few key points to keep in mind. The main question we wanted to answer was, how many input frames are needed to train the network before it can automatically detect blotches on the unseen frames? This is crucial because it determines how much manual work a restorer needs to do before the system can take over and run automatically afterwards. And just as important, this approach fully respects copyright, since the training only uses frames that the restorer has already manually restored previously. So when training a model, we usually split the data into three sets: training, validation, and test set. The validation set is used to fine-tune the model's parameters and help prevent overfitting. But in the experiment, we wanted to have overfitting as it let us see how the model learns from using different amounts of data. So to understand how the model behaves, we ran tests using 20, 40%, 60%, and 80% of the input frames, all for the first instance without applying motion compensation. This way, we can clearly observe how the model's performance improves as more training data becomes available. So to perform the motion compensation, the network needs three frames: the previous frame, the current frame, and the next frame. In practice, these three frames are converted into black and white, stacked together, and fed into neural network. This allows the network to encode temporal information, which is crucial for motion analysis. And remember, some features in a frame may look like blotches, but aren't actually defects. So by analyzing multiple frames together, this network can distinguish real blotches from the scene feature. Finally, we wanted to test how cropping the frame affects the computational power. And the approach is very simple. We divide each frame into multiple smaller pieces, just like this. By processing smaller regions instead of the full frame, the model requires less memory and consumption and computation consumption, which can significantly improve the speed in the processing. So since our goal was to have a small DNN, we aim for a reduced number of parameters. In our case, we kept at 3 million parameters, because even in the smallest version, we had 3.5 million parameters. And the average of pre-trained network can go up to 92.6 million parameters, which is far beyond what we wanted for a lightweight model. So now let's move on to our results. So here we compare the best performing SDIp algorithm at its optimal threshold with the best performing DNN also at its optimal threshold. As you can see, the DNN's predictions are much closer to the ground truth, and the SDIp method can detect the blotch, but it doesn't fully cover it. So this comparison was for our uncompressed frame. Next, we'll look how the model performs on a compressed frame. So we can see here clear differences. For the carrier frame, so the compressed frame, the SDIp produces many false positives, while the DNN is much closer to the ground truth. And the same trend appears with the night sequence, although some false positives remain. This is happening because, likely because the frame is heavy compression, which reduces the available information. But yet the DNN still outperforms the SDIp and aligns more closely with the ground truth, which indicates a room for further improvement with fine-tuning. So now let's look at looking at the motion compensation. We can see a clear improvement in detection across all data sets. Both detection accuracy increases and false positives decrease significantly. Now let's look at some visual results, starting with the uncompressed synestheta frames. As you can see, the version with the motion compensation has far fewer false positive pixels compared to the version without it. In this example, the improvement is very clear. Motion compensation makes the detection much cleaner and closer to the ground truth. This shows how adding temporal information can significantly improve the quality of blotch detection. Now let's look at the carrier and the night sequences, so the compressed frames. For carrier, it's a bit hard to see on the screen, but the version with motion compensation still performs better than the one without it. And there are fewer false positives, especially in the upper part of the frame. For the night sequence, so the compressed and the smaller frames, motion compensation makes the blotch masking more comprehensive. However, some false positives are still visible, likely due to the heavy compression again and the lower resolution of these frames. So overall, we can say that motion compensation consistently improves detection, even on challenging and compressed data. Now let's look at the effects of cropping the frame. Cropping the frame reduced the memory usage by about 90%, which greatly improved the efficiency. However, at this time, it comes at the cost with increased false positives. This is likely due to the imbalance in the training data, where the model sees more clean region than blotches. So a straightforward solution is to sort the cropped image into two groups, blotch and non-blotch, and then train the network with a 50-50 balance. That way, the model learns to recognize blotches more effectively and make better distinction during detection. Here, we have the visual result for the crop frames, shown at the bottom right. For synestheta, visually, the reconstructed binary mask is fairly close to the crop version. However, it doesn't cover all blotches and doesn't reduce the number of false positives. For the carrier sequence, blotches are detected, but there are still many false alarms. This may be because some of the blotches are very light in color, making them harder to distinguish in the crop low-resolution input. And now the RSC curve for each sequences. We plotted different DNN version in green and the SDIp algorithm in red. So remember, the higher up and the further left the curve, the better the performance is. To put into perspective, imagine a 4K image with about 8.3 million pixels. If the false positive rate is just 1 in 100,000, that's only around 80 pixels falsely detected, which is hardly noticeable. So that's why keeping the curve as far as left as possible is important. So we can see that Cinecita is the one that stands out as the best one. So to conclude, neural networks significantly outperform a traditional algorithm even when trained with just 1,500 frames. And real blotches can be detected efficiently using lightweight model with fewer than 3 million parameters. So future work could improve data sorting for crop frame, as I mentioned earlier, and we can also incorporate in-painting techniques for automated restoration for the next step. So we can think of diffusion model, for example. And that's it. Thank you very much for listening. Merci.